Hello, this is Michał Wójcik here, and I welcome you again to my series of lectures, Physics for Amateurs. Today we will talk a bit about Lagrangian's formulation of classical mechanics. Before we will go to that, let me summarize what we have done on the previous lecture. So we were considering n particles with the trajectories. So we consider a function from time to, in fact, 3n dimensional space, but obviously it just depends on how we picture it, because all these particles move in standard 3D space. So all of these vectors are three-dimensional vectors dependent on time. But as a mathematical formulation of the problem, we can put all coordinates from all of these particles in one big 3n dimensional space. And we had potential energy, which we denoted as V. And we noticed that if we define force using V as a derivative of position, V was dependent on position, solely on position. Then, if we calculate the work which was done by forces in this system, when we are moving particles from one configuration, which in this case means from one positions to the other, the energy, the total work done by forces is equal to the difference of V of the starting state and ending state. This is just a mathematical property of the situation when the force is equal to minus is just a convention, derivative of V with respect to position. As you probably remember, we defined derivative in a way that if we take derivative with respect to vector, it just means that our resulting derivative has the number of coordinates as the vector, and on each coordinate we place a derivative which is simply a derivative of this coordinate. And that's why this makes sense, that derivative of V with respect to position is a force which has the same number of dimensions as position. And if in our case we consider an abstract position of 3D dimensions, force obviously has also 3D dimensions, but we might here in writing, we just took a derivative with respect to one set of 3D coordinates for each particle separately. So we are considering a force which acts on a ith particle. in our example, we considered a special potential energy which is equal to multiplication of masses and certain constant, which happens to be gravitational constant, and divided by the distance between two trajectories. It turned out in a previous lecture that when we calculated the derivative of v with respect to particular position coordinates, by particular I mean connected to the relevant particle, in this case ith particle. So when we calculated this derivative with respect to this ith set of coordinates, we got a force which is a sum of all forces which acts on this particle from the other particles according to the Newton gravitation law. So that simply means that in this V we encoded the whole Newtonian gravitational law, the law of how gravity attracts objects. And by saying that force is a derivative of this V with respect to position, it's practically the same as formulating this famous Newton's law of universal gravitation. Now, when we know the force which acts on a particle, which is in this case, if we have n particles, all forces that we consider are gravitational, so then obviously the force which acts on one particle is a sum of forces from all other particles according to the law of gravity. And when we have these forces, we might wonder what will be the trajectories of our particles. Can we calculate trajectories? If we take a standard Newtonian formulation of mechanics, we know that there is a dependence between force and acceleration. Acceleration is a second derivative of time from the position. So when we multiply a mass of an object by acceleration, which is the second derivative of time of position, we have force. So knowing forces and knowing masses of our particles, we know acceleration at a given time. Now, when we know acceleration, and we know a position, and we know velocity of particle, we can solve this kind of differential equations and retrieve the trajectories of all particles. But we will be not doing this, and this problem is complicated and it doesn't have analytic solution when the number of particles is more than 2. We will not solve it, but we will use this to show another formulation of mechanics, because for now we just talked a bit about Newtonian formulation of mechanics. But there is other formulation of mechanics, which is Lagrangian formulation, and it is particularly useful to know it because later a lot of physics is built on this formulation, even if we will go to relativistic theories and quantum mechanics theories, we will be using Lagrangian formulation of mechanics, especially in quantum field theory, but we will go to that later. So now let's remember our potential energy V. It is written here as well. We will postulate or require or define. We will define a value L, which will be a very abstract value for now, for our mechanical system with n particles, for which we can know their position at a given point of time and their velocity. We will define a value which we will denote as L, and this value will be defined like that. Take a velocity of particle I, square it, multiply by mass of particle, add all together, divide by 2, and this is, if you remember from school, it's a kinetic energy of particles. And then subtract from this the potential energy that we know from our previous reasoning. But let's forget for a moment that this is potential energy. Let's forget that this is kinetic energy. We just have certain value which depends on position and velocity. The position is hidden here. This is a distance between particle I and j. And we do summation over all indexes, which in fact over all pairs of particles, and we don't repeat a pair. So this is why here it's only for j's, only for i's which are less than j. So we have this value which depends on position and velocity of our particles. And we forget everything about it. It's just abstract value. And for this abstract value, which depends on positions and velocities, we might formulate a rule. Imagine that we know that our particles will be in one particular configuration at time point A. By configuration, we mean that we know their positions and velocities. And now we may wonder how the situation will evolve. What will be the trajectory of all particles? And we can formulate this in a way that the trajectory should be a stationary point of the integral from A to B along the path. So the path which has a stationary integral is the one which will be our physical evolution of the system. What does it mean stationary? That means that if we take an infinitesimal disturbance of our trajectory, the difference between the value of this integral for the trajectory and the value of this disturbed trajectory will vanish, in the meaning that normally you would expect that the infinitesimal, we think here about infinitesimal of the first order, infinitesimal of the first order difference on the trajectory will cause some infinitesimal difference of this integral. But if the trajectory is stationary, the infinitesimal difference of the trajectory makes zero difference for the total integral along the path. Zero in terms of infinitesimals of first order. There might be some values of further orders, like the second order, third order, etc., but they will be not of the first order. So that means that we calculate this difference for an infinitesimal disturbance of the trajectory, and we know that this difference should be zero. So actually, it turns out that from this condition we can formulate equations which will bind partial derivatives of L in certain way. So let's start. So by delta S, we just means this infinitesimal difference between action, which is calculated on the path, and the path which is slightly disturbed. And the disturbance is of a particular kind that we assume that at time point A and at time point B, the disturbance is zero. So it only disturbs the trajectory between points A and B. At the ends of the trajectory that we consider, trajectory is undisturbed. And for this disturbance with this condition, we expect difference of the action to be zero, because we want our trajectory to be stationary. So we assume this is zero and we start to calculate this. And we calculate this using an approximation, but we can do this assuming this is an infinitesimal value, approximating by derivatives. So we take the derivative of L with respect to Q, and we multiply this times this position disturbance. Just mind that this is vector derivative, because Q is a 3n dimensional vector. But this is what L depends on. It depends on position Q and time derivative of Q, which is marked as Q with this dot. But this first argument is position. So derivative of position is a long vector, and displacement is also a vector, and it is also a vector of 3n dimensions, so this is a scalar multiplication. And then we add derivative of the second argument, which is where we have time derivative of q in our equations, and then we multiply it by the disturbance of time derivative of q. This is just a regular approximation when we take a difference of values of the function at a very close arguments. We use derivative to approximate the values of this function, and this is just in a way as we usually do this. Now, if we look at this expression, this is derivative of this small delta q disturbance. If we remember how we calculate derivative of multiplication, this is derivative of the first part of the first term in multiplication times second part of multiplication plus first part of multiplication times derivative of second part of multiplication. We can take a derivative of time from multiplication of these terms and subtract from this derivative of time of the first term times second term, and that will be exactly this. Now, this is integral from derivative. So this is simply a difference between this at point B and this at point A, but we have chosen our disturbance of the trajectory in a special way that it is 0 at point A and B. That's why this part is equals to 0. So we have only this which is significant here. So we have this integral over this partial derivative of L with respect to Q, which means all positions, and time derivative of partial derivative with respect to velocities, times our small infinitesimal disturbance of trajectory, which is arbitrary. But if it's arbitrary, we can imagine that it will disturb only slightly around given point of the trajectory. So that means that the term in brackets needs to be 0 at all points of the trajectory to have this integral equal to 0. And that's how we derive Euler-Lagrange equations, which says that this partial derivative form needs to be equal to 0 along our stationary trajectory. So once again, what we did here, we took a very abstract value which depends on positions and velocities, and we defined action functional, this is called action functional, as an integral of L along the path. And we said that we defined the physics of our system in a way that we said that we believe that particles will move in a way that their trajectories will be stationary with respect to this action integral. And then we did calculations based on that assumption that the path will be stationary, and it turned out that along stationary path, partial derivative of L with respect to position minus time derivative of partial derivative of L with respect to velocities needs to be equal to 0. And this is Euler-Lagrange equation. Obviously, it has nothing to do that the value of L was defined in this way, this particular way. That was just an example, but because of this example, we could easily understand what type of object it is. We will go back to this. We will go back to this later. Now, if we know that this least action, well, it's not necessarily least action principle. It is a stationary action principle. So for stationary trajectory, we have this equation. And now we might consider what this equation really means, because it looks very abstract. In fact, it doesn't resemble at first sight a Newtonian law of motion. But it will lead to that, and I will show you this very, very shortly. Once again, recall how we defined L. We take kinetic energy and we subtract potential energy for the gravitational forces. But we will be a bit more generic than that. We will take kinetic energy exactly as we have written it, as a square of velocity times mass divided by 2, and obviously sum them up for all particles. That will be the part which will be here. We will call this T. But for the potential energy part, we will require only that this is some function V which depends on positions. So we will simply take a particular case, but a very important case, of Lagrangian, which can be written as kinetic energy minus potential energy, which is dependent purely on positions. Particular example of that is obviously our gravitational case with gravitational potential energy. But as I said, we will consider a bit more generic case. And in that case, obviously L is equal to T minus V. Now, if we rewrite Euler-Lagrange equation with that in mind, this first part will become derivative of V with respect to position, with respect to Q. Why is that? Because L is equal to T minus V. T depends purely on velocities. V depends purely on positions. So, derivative with respect to positions from L will be only V, will be only a derivative of V. And what is minus derivative of V with respect to Q? In our previous in our previous considerations that was force. But we don't need to remember now that this is force. It will come out of the equations. Just wait for it. So this is this first part. The second part, derivative of time from partial derivative of L with respect to velocities, which are here. Again, that will be only derivative of t, because only part t is dependent on velocities. V is dependent on positions. So we have this kind of equation as a result of this equation if we assume that our L has this kind of form. So that simply means that time derivative of this partial derivative of t with respect to velocities is equal to minus partial derivative of v with respect to positions. Now, we know what this is because our kinetic energy is given explicitly. So we can calculate this. The derivative of this with respect to position is simply, this is square, so in derivative there is without square, and this 2 we take as a factor of multiplication, but we have 1/2 here, so 2 is cancelled with 1/2. And if we consider the ith particle for this derivative, because remember obviously that the whole derivative of t with respect to q is a very long 3n dimensional vector, we consider here only 3 coordinates of this vector which are associated with particle I. So for this particle I, this derivative is obviously m mass I times velocity of particle I. And we take time derivative of this, which is obviously acceleration. The right side of the equation is still the same. But what is this? Mass times acceleration is force. So now we know that if we have Euler-Lagrange equation satisfied along the path, and our Lagrangian is of this form, we know that this derivative of v with respect to position is force. So now this is a very important moment. We assumed only that our L has the form t minus v, and we assumed that we want our path to be a stationary trajectory, our trajectory to be a stationary trajectory of action for this Lagrangian. From that it follows that partial derivative of v with respect to position is force. And that shows, in fact, the power of Lagrangian formulation of mechanics, because we know from our previous considerations that for this particular gravitational example, if we take force as v, it gives us exactly, if we take force as partial derivative of v with respect to position, it gives us Newton's law of gravitation. So we showed how to define Newton's law of gravitation in terms of Lagrangian formulation of classical mechanics. One more thing to show today is a energy conservation law. We will be interested in this specific formula, which is L minus partial derivative of L with respect to velocities times velocities. And times here, multiplication is obviously scalar multiplication. Once again, I will remind you this partial derivative with respect to Q is a very long vector with dimensionals exactly equal to dimensionals of Q. We will consider time derivative of this expression, and we will show that this time derivative is 0, which means this expression is constant. And we will do this under the assumption that our Lagrangian doesn't depend on time. And this is exactly the case in our example. If you take our example, Lagrangian depends on positions in that way, depends on velocities, but it doesn't depend separately on time. Obviously, time plays a role in the equation because we can calculate knowing the trajectories of particles, we can calculate position for a given time, and we can calculate velocity for a given time. But time doesn't enter into the Lagrangian equation in any other way than through velocity or position. It could be, in theory, that we might write here something like plus t, right? It wouldn't have much physical sense, but we could do this. And then L would depend on t directly. This is not the case. In our case, L depends only on positions and velocities. So under this assumption, which we noted symbolically here like this, we will do our calculation. So we calculate the time derivative of L, which obviously we need to take all variables, calculated time derivative of multiply times partial derivative according to the chain rule, which is this is done for L, and here we apply a law of derivative of multiplication. So we calculate derivative of the first part, we leave the second part unchanged, which is derivative of Q, and then we leave the first part unchanged, and we calculate time derivative of Q with dot, which is Q with two dots, which means second time derivative of Q. As you can notice, this part and this part cancel themselves out, which leaves us only with this part and this part, and they have Q dot in common here, so we can take it out of the bracket. And what is in the bracket? In the bracket we have Euler-Lagrange equation, which we know that along the path, along the trajectory, which is our stationary trajectory, it is 0. So along stationary trajectory, our expression L minus partial derivative of L with respect to velocities times velocities is equals to 0. Time derivative of this. If time derivative of this is 0, that means that this expression is constant in time. Now, let's see what this expression is when we recall that our Lagrangian has this specific form t minus v, where where t is dependent on velocities and v is dependent on positions. So the derivative of t with respect to velocities is obviously the same as derivative of t with respect to positions, because I will note it here once again, because just for you to so L is t minus v. So derivative of t with respect to velocities, derivative of L with respect to velocities is just derivative of t with respect to velocities, because v depends only on positions. And we leave here derivative of velocities unchanged. What is this? This is because remember, the multiplication is scalar multiplication, so we can always denote it as a sum over all particles multiplied again scalar multiplication, but this is only 3D scalar multiplication now. So we added n scalar multiplications for each particle separately, but now this derivative of t is kinetic energy, remember. So derivative of t with respect to velocities is simply a mi times velocity, because it was velocity square divided by 2. 2 cancel out, we have only this, but remember here is our velocity, so we multiply this times velocity, so we have mass times velocity squared, which is equal exactly to 2t. Then we know that L minus 2t is a constant value along our stationary trajectory. But obviously I have this written here. But obviously L is equal to t minus v. So if L minus 2t is constant, that means that t plus v is constant, because that's L is t minus v, so t cancels with 1t, we have minus v, minus t is constant, which is the same as t plus v is constant. But t was kinetic energy and v was potential energy. We obviously don't know till that point that this is potential energy. It was just our v, which we showed its relation between partial derivative of v with respect to position and force. In fact, that gives us a notion of potential energy, because we can prove, using the reasoning that we used in the previous lecture, that energy that forces doesn't depend on the trajectory, it only depends on the value of potential energy at the end and at the beginning of the trajectory. So we know in fact that this is potential energy in that sense. But from Euler-Lagrange equations, it follows now that t plus v is constant along stationary trajectory, which simply means that an energy is conserved, that the kinetic energy plus potential energy is a constant value along the stationary trajectory, which means that energy is conserved along stationary trajectory. So we showed two important facts from Euler-Lagrange formulation of classical mechanics. That if we have this kind of Lagrangian, we know that the force is equal to minus partial derivative of v with respect to positions, which gives us Newtonian law of motion. And we know that energy is conserved along the stationary trajectory. So that shows us that it is to formulate the physics of a given system, it is enough to find the Lagrangian, and then everything follows from the principle that particles follow the stationary trajectory. The stationary, obviously in this precise meaning, that this trajectory is an extreme trajectory of this integral. And that would be all for today. I hope you enjoyed. I hope I managed to demonstrate you the power of Lagrangian formulation of classical mechanics. Thank you.